Hello there, and welcome to Sleepy Answers. Tonight, we are drifting into one of the most enchanting mysteries of human existence, the question of why we fall in love. It is a question that has captivated poets and philosophers for millennia. Yet only recently has science begun to unveil the intricate choreography of chemicals and neural pathways that orchestrate this profoundly moving experience. As you settle into this gentle exploration, I invite you to let your thoughts wander through the hidden landscape of the brain, where invisible molecules shape our deepest connections and most powerful emotions. If you find comfort in these quiet journeys through science and wonder, I encourage you to like and subscribe. It helps others discover this peaceful corner where curiosity meets calm, one sleepy soul at a time. But for now, simply rest. Allow your breathing to slow. Let your body sink deeper into comfort. And together, let us explore the beautiful chemistry of falling in love. Love is not merely an abstract emotion floating somewhere in the ether of human consciousness. It is a tangible cascade of neurochemicals, a symphony of brain regions, communicating in precise harmony, an ancient biological program written into our very cells. When someone says they are falling in love, they are describing an actual phenomenon happening inside their skull. A transformation as real as any physical change their body might undergo. The brain in love resembles the brain under the influence of certain substances, activated in patterns that echo addiction, obsession, and profound reward. Yet this particular intoxication serves one of evolution's most critical purposes, bringing two people together with enough force to overcome the challenges of forming a lasting bond. The experience begins long before we consciously recognize it, before words are exchanged, before names are known, before intentions are stated. The body has already begun its quiet assessment. Ancient circuits deep within the brain are evaluating, measuring, calculating possibilities. Hormones shift. Neurotransmitters adjust their flow. The stage is being set for something that might last a few weeks or might endure a lifetime. Understanding this process does not diminish its beauty. Rather, it reveals a kind of elegance in how evolution has woven together sensation, emotion, cognition, and chemistry into an experience that feels both utterly unique and profoundly universal. The three stages of love. Scientists who study the neurobiology of romantic attachment have identified a framework that helps us understand love's progression through distinct stages, each governed by its own constellation of chemicals and neural circuits. This framework, developed through decades of research and popularized by biological anthropologist Helen Fisher and her colleagues, divides romantic love into three overlapping but distinguishable phases: lust, attraction, and attachment. Each phase serves its own evolutionary purpose. Each creates its own unique internal experience, and each is mediated by different systems within the brain and body. Lust represents the most primal layer of romantic experience. It is driven primarily by the sex hormones testosterone and estrogen, which exist in both men and women, though in different concentrations. This is the raw, physical craving that draws us toward potential partners based largely on sexual desire. lust can exist entirely independently of the other stages. We can feel intense physical attraction to someone we barely know, someone we might not even particularly like as a person. This separation reveals something important. Lust is fundamentally about reproduction, about the body's drive to seek out opportunities for genetic mixing. The brain regions most active during this phase include the amygdala and the hypothalamus, ancient structures that regulate basic drives and emotional responses. When lust is engaged, the body responds with a cascade of physical changes. Blood flow increases to certain areas. Heart rate elevates slightly. Pupils may dilate, a response that makes us appear more attractive to others, while also allowing us to take in more visual information about the person before us. Even our skin temperature can shift, creating that sensation of warmth or heat that people describe when they feel a strong physical attraction. These changes happen largely outside conscious control, orchestrated by the autonomic nervous system responding to the presence of someone our deeper brain systems have identified as a potential mate. But lust alone rarely sustains a relationship. For that, something deeper must emerge: attraction. This is the phase that most people associate with falling in love, that obsessive, all-consuming preoccupation with another person. During the attraction phase, someone becomes not just sexually desirable, but uniquely special, irreplaceable, fascinating beyond all reason. Hours can vanish while thinking about them. Sleep becomes difficult because the mind keeps returning to memories of their voice, their face, the way they move through space. This is when romantic love reveals its addictive quality, when the reward circuits of the brain become hijacked by thoughts of one particular person. The neurochemical signature of attraction is dominated by three key players: dopamine, norepinephrine, and serotonin, though serotonin's role is somewhat paradoxical, as we will explore later. Dopamine floods the brain's reward pathways, creating sensations of euphoria, energy, and focused attention. Norepinephrine amplifies alertness and arousal, contributing to racing thoughts and the physical symptoms of nervous excitement. Together, these chemicals can make the early stages of romantic love feel thrilling and slightly dangerous, like standing at the edge of something vast and unknown. The brain regions most activated during attraction include the ventral tegmental area and the caudate nucleus, both part of the brain's reward circuitry. These are the same areas that light up in brain imaging studies when someone experiences pleasure from food, from winning money, or from using addictive drugs. When we look at a photograph of someone we have just fallen in love with, these regions surge with activity, flooding the brain with dopamine and creating a powerful association between that person's image and the sensation of reward. Over time, this association becomes deeply embedded until merely thinking about the person can trigger a rush of pleasurable feeling. Finally, there is attachment, the stage that allows romantic love to deepen and endure over months, years, even decades. This is where the initial intensity of attraction evolves into something calmer, but no less significant. A profound sense of bonding, comfort, safety, and partnership. Attachment is governed primarily by two neuropeptides, oxytocin and vasopressin. These chemicals are released during physical intimacy, during moments of emotional connection, and during times when partners support each other through difficulty. They work to create lasting neural changes that bind two people together at a fundamental level. Oxytocin, often called the bonding hormone, is released during physical touch, during sexual activity, and even during the moments of deep emotional connection or eye contact. It promotes feelings of trust, reduces anxiety, and strengthens the neural pathways that associate a particular person with comfort and safety. Vasopressin works in parallel, particularly in men, promoting pair bonding and a protective, possessive instinct toward one's partner. Together, these chemicals help transform the frantic energy of early attraction into the stable, enduring connection that characterizes long-term relationships. These three stages do not always progress in linear order. One might feel deep attachment to a friend for years before suddenly experiencing attraction. Lust might arrive first, followed only later by genuine attachment. Different relationships emphasize different combinations of these stages. Understanding them as separate but interconnected systems helps explain the complexity of human love, why it can take so many forms, why it can feel so different from one relationship to another, why it can surprise us with its intensity or confuse us with its absence. The initial spark, first impressions and chemistry. The moment when two people first encounter each other contains a remarkable amount of rapid, unconscious processing. In the span of seconds, sometimes milliseconds, the brain makes assessments that will shape whether attraction might develop. This initial evaluation draws on every sense simultaneously, creating a composite impression that occurs far below the level of conscious awareness. By the time we form a conscious thought about someone, the deeper regions of our brain have already begun their analysis. Visual information arrives first, processed by the occipital lobe at the back of the brain, before being sent to regions that evaluate faces, bodies, and movement patterns. Humans are extraordinarily sensitive to facial features, able to detect asymmetries measured in fractions of a millimeter, able to read micro-expressions that last mere moments. Research suggests that certain facial proportions are consistently rated as more attractive across cultures, possibly because they signal health, fertility, or genetic quality. Clear skin, symmetrical features, certain ratios of facial width to height. All of these factors are evaluated rapidly and automatically. But visual attraction goes far beyond static features. Movement patterns matter enormously. The way someone walks, the fluidity or awkwardness of their gestures, the timing of their smiles. All of these provide information that the brain uses to assess compatibility. Studies have shown that people can identify the gender and even estimate the attractiveness of others based solely on biological motion, watching point light displays that show nothing but the movement of major joints. This suggests that attraction to movement patterns is deeply embedded in our perceptual systems, likely because movement reveals information about health, confidence, and physical capability. Simultaneously, other sensory channels are gathering their own information. The auditory system is analyzing vocal qualities, pitch, rhythm, resonance, pace. Women tend to find lower-pitched male voices more attractive, possibly because lower pitch correlates with higher testosterone and larger body size. Men often find higher-pitched female voices attractive, a preference that may relate to perceptions of youth and fertility. But voice attractiveness is about more than pitch alone. Warmth, expressiveness, the musicality of speech patterns, all of these contribute to whether someone's voice appeals to us or leaves us indifferent. Then there are the chemical signals, operating almost entirely outside conscious awareness. From the moment two people come within a few feet of each other, molecules are traveling through the air between them, carrying information that the olfactory system will decode. Every human body produces a unique scent signature, influenced by genetics, diet, hormones, and the particular bacteria that colonize our skin. These scents are detected by receptors in the nose and sometimes by a small organ called the vomeronasal organ, which some researchers believe may still function in humans to detect pheromones, though this remains a topic of active scientific debate. Within the first few moments of meeting someone, all of this sensory information converges in brain regions that must rapidly answer a fundamental question. Is this person someone who might be worth pursuing? The amygdala evaluates emotional valence, determining whether the person feels safe or threatening. The prefrontal cortex begins forming judgments about compatibility based on whatever cues are available. The reward system starts to respond, or it does not, to the overall constellation of signals. And crucially, the brain begins checking whether this person's presence creates pleasure, curiosity, or interest. The early warning signs that attraction might be possible. This initial evaluation happens so quickly that most people are not aware it is occurring. They meet someone and feel an immediate spark, or they do not. They describe it as chemistry, as clicking, as an instant connection or an instant lack thereof. What they are really describing is the result of the multiple brain systems rapidly processing a flood of sensory information and delivering a verdict. This person is interesting, or this person is not. Sometimes this verdict is wrong. Sometimes people we initially overlook become deeply attractive once we know them better. Sometimes people who seem irresistible at first prove disappointing upon further acquaintance. But in those first moments, the brain is doing its best with limited information, running ancient algorithms designed to help us identify promising potential partners as quickly as possible. Interestingly, stress and context can dramatically influence first impressions. Meeting someone in an exciting or mildly frightening situation can amplify feelings of attraction, a phenomenon psychologists call excitation transfer. The elevated heart rate, the surge of adrenaline, the heightened alertness created by the situation can be misattributed to the person we are with, making them seem more attractive than they might appear in a calmer context. This is why dates involving adventure or mild risk, rock climbing, horror movies, roller coasters, can sometimes accelerate romantic feelings. The body's arousal system does not distinguish very well between fear and attraction, between excitement and romance, and the brain sometimes confuses the source of its own activation. Dopamine and the reward system. Of all the neurochemicals involved in romantic love, dopamine occupies the most central position. This molecule, a neurotransmitter that carries signals between neurons, is fundamental to how we experience pleasure, motivation, and reward. It is the chemical that tells your brain, "This matters. Pay attention to this. Seek more of this." And when you fall in love, Dopamine floods through neural pathways in quantities that rival or exceed what occurs during some of the most pleasurable experiences humans can have. The dopamine system originates primarily in two small clusters of neurons deep in the midbrain, the ventral tegmental area and the substantia nigra. From these origins, dopamine-producing neurons extend their projections throughout the brain, reaching regions involved in motivation, emotion, memory, and motor control. The most important projection for understanding romantic love is the mesolimbic pathway, which connects the ventral tegmental area to the nucleus accumbens and other structures that comprise the brain's reward circuit. This is the pathway that becomes supercharged when you are falling in love. Brain imaging studies using functional MRI have repeatedly shown that when people who are intensely in love look at photographs of their beloved, the ventral tegmental area and caudate nucleus light up with activity. These regions show patterns of activation remarkably similar to what occurs when someone uses cocaine or other addictive drugs. This is not metaphorical. The brain in love is genuinely experiencing a form of chemical reward that resembles addiction. The person we love becomes associated so strongly with pleasure and reward that thinking about them, seeing them, or being with them triggers a powerful dopamine response. This dopamine surge creates several distinct effects that characterize the early stages of romantic love. First, it generates euphoria, that sensation of floating, of everything being brighter and more vivid, of the world suddenly feeling full of possibility. People in the throes of new love often describe feeling energized, needing less sleep, feeling capable of anything. This is dopamine at work, enhancing mood and creating a positive emotional state that colors perception of everything, not just the beloved, but the entire world. Second, dopamine creates focused attention and motivation. When the reward system identifies something as important, it orients all of your cognitive resources toward it. This is why falling in love makes it so difficult to concentrate on anything else. The brain has essentially decided that pursuing this relationship is the most important task at hand, more important than work, than other friendships, than hobbies or responsibilities. This intense focus can be overwhelming, but it serves a crucial evolutionary function. It ensures that we invest the time and energy needed to actually form a bond with a potential partner, rather than being distracted by other opportunities. Third, dopamine contributes to the formation of powerful memories associated with the beloved. The hippocampus, a brain structure essential for memory formation, is richly supplied with dopamine receptors. When dopamine levels are high, memories form more readily and more vividly. This is why we tend to remember in exquisite detail the early days of a relationship. The first conversation, the first touch, the first kiss. These memories are encoded with an emotional intensity that makes them remarkably durable, sometimes lasting a lifetime with a clarity that memories of other events from the same period lack. Fourth, and perhaps most significantly, dopamine creates craving. This is where the addiction metaphor becomes particularly apt. The reward system does not just register pleasure when the reward is present. It also generates anticipation and desire when the reward is absent. When someone you love is not with you, the dopamine system is pushing you to seek them out, to make contact, to recreate the it, conditions that will trigger another release of dopamine. This is why people newly in love constantly check their phones, why they feel anxious when messages go unanswered, why they structure their entire day around the possibility of seeing or talking to their beloved. The anticipation phase is actually more powerful than the reward phase in many cases. Brain imaging studies show that dopamine activity peaks not when we receive a reward, but in the moments just before we expect to receive it. This is why the period leading up to a date, the moment before a text arrives, the anticipation of seeing someone we love can feel even more intense than the actual encounter. The brain is running simulations, imagining the upcoming pleasure, and flooding itself with the dopamine in response to these mental previews. Interestingly, uncertainty amplifies the dopamine response. When rewards are unpredictable, when we cannot be sure whether we will receive them, the dopamine system becomes even more engaged. This helps explain why relationships that are unstable or inconsistent can sometimes feel more addictive than secure ones. The brain's reward circuitry is maximally activated by variable schedules of reinforcement, the same principle that makes gambling addictive. When we cannot quite predict whether someone will text back, whether they will be affectionate or distant, whether they are truly interested or merely being polite, the uncertainty keeps the dopamine system in a state of heightened activation. Over time, if a relationship continues, the dopamine response typically moderates. The initial rush becomes less intense, not because love diminishes, but because the brain adapts to the presence of consistent reward. This is a normal process called habituation. The dopamine system is designed to be most responsive to novelty, to new sources of pleasure, to unpredicted rewards. As a relationship matures and becomes more predictable, the dopamine high of early attraction naturally subsides. This is often when couples worry that they are falling out of love. But what is actually happening is a transition from the dopamine-driven attraction phase to the oxytocin-mediated attachment phase, a transition we will explore more deeply later. The stress hormones of early love. While dopamine creates the euphoria and excitement of falling in love, another set of chemicals contributes to the anxiety, nervousness, and obsessive quality that characterizes new romance. Falling in love is not just pleasurable, it is also stressful. The brain perceives the uncertainty and vulnerability of opening oneself to another person as a kind of crisis, and it responds by activating the body's stress response system. This activation is responsible for many of the physical symptoms people experience when they are around someone they are falling in love with. Racing heart, sweaty palms, butterflies in the stomach, difficulty sleeping, loss of appetite. The primary stress hormone involved in early romantic love is cortisol, produced by the adrenal glands in response to signals from the hypothalamic pituitary adrenal axis, the brain's central stress regulation system. Research has shown that people who have recently fallen in love have elevated cortisol levels compared to single individuals or those in long-term relationships. This elevation is not subtle. The differences are measurable and consistent across studies. Interestingly, the cortisol elevation is temporary. When the same couples were tested again 12 to 24 months into their relationships, their cortisol levels had returned to normal. This suggests that the stress response is specific to the early, uncertain phase of romantic love, when the outcome of the relationship is still unknown. Why would evolution design romantic love to be stressful? The answer likely relates to motivation and attention. Moderate stress keeps us alert, focused, and motivated to resolve the source of uncertainty. When cortisol is elevated, we are more attentive to threats and opportunities, more vigilant about social cues, more motivated to take action to reduce the uncertainty. In the context of early romance, this means we are more likely to pay careful attention to the other person's signals, to invest effort in presenting ourselves well, to take the risks necessary to move the relationship forward. The stress keeps us engaged during a critical period when the relationship is still fragile and could easily fail. Working alongside cortisol is norepinephrine, also called noradrenaline, a neurotransmitter that functions both in the brain and in the body's sympathetic nervous system. Norepinephrine is responsible for the physical arousal symptoms of attraction: the elevated heart rate, the slight trembling, the rush of energy, the heightened sensitivity to stimuli. When you are around someone you are falling in love with, your brain releases norepinephrine, which activates your body's fight-or-flight response in a mild but noticeable way. This might seem counterintuitive. Why would the same chemical system involved in fear and danger activate during romantic attraction? The answer lies in how the nervous system is organized. The brain has a limited set of neurotransmitter systems to work with, and it often repurposes them for multiple functions. Norepinephrine's role is to prepare the body for action, to heighten awareness and responsiveness. In the context of danger, this manifests as fear. In the context of attraction, it manifests as excitement. The physical sensations are remarkably similar, hence the racing heart, the butterflies, but the cognitive interpretation and emotional context are entirely different. Norepinephrine also affects memory formation, working in concert with dopamine to ensure that experiences related to the beloved are encoded with particular vividness. This is part of why we remember early romantic experiences so clearly. The combination of dopamine and norepinephrine creates optimal conditions for memory consolidation. Every conversation, every gesture, every shared moment gets stamped into memory with unusual clarity, building a rich store of experiences that strengthen the emotional bond. The combination of elevated cortisol and norepinephrine also contributes to some of the less pleasant aspects of early love. Anxiety increases. Sleep can become difficult, with racing thoughts making it hard to fall asleep or causing frequent waking. Appetite may decrease, as stress hormones suppress hunger signals. Some people experience a kind of constant, low-level tension, a background hum of nervousness that persists even when things are going well. This is the body interpreting the vulnerability of new love as a form of stress, mobilizing resources to deal with what it perceives as a challenge or threat to well-being. Interestingly, these stress responses are not uniform across individuals. People with more secure attachment styles, who learned in childhood that relationships are generally safe and reliable, tend to experience lower levels of anxiety when falling in love. People with anxious or avoidant attachment styles may experience more intense stress responses, sometimes to the point where the anxiety becomes overwhelming. This variation suggests that while the neurochemical systems of love are universal, our personal history and psychological makeup shape how we experience and respond to these chemical changes. The stress of early love serves another important function. It makes us cautious and attentive. When we are nervous around someone, we are more likely to think carefully before we speak, to monitor the other person's reactions, to adjust our behavior based on feedback. This social vigilance, though exhausting, helps prevent misunderstandings and mistakes during the delicate early phase of a relationship. The stress keeps us from becoming complacent, from taking the other person for granted, from assuming the relationship is secure before it actually is. As relationships mature and the initial uncertainty resolves, stress hormone levels decline. The body essentially learns that this relationship is not a crisis, but a source of support and comfort. When this transition occurs, the experience of love shifts dramatically. The anxiety fades. Sleep improves. The constant preoccupation lessens. But importantly, this reduction in stress does not mean love has diminished. Rather, it signals that the relationship has successfully transitioned from the uncertain attraction phase into more stable attachment. The chemicals of love are changing, but love itself continues. Serotonin and obsession. While dopamine and stress hormones create the pleasure and anxiety of early love. Another neurotransmitter plays a particularly fascinating role: serotonin. Paradoxically, falling in love is associated not with an increase in serotonin, but with a decrease. Research comparing people who have recently fallen in love with single individuals and those in long-term relationships has found that the newly in love show significantly lower serotonin levels. This finding is particularly intriguing because low serotonin is also characteristic of obsessive-compulsive disorder, a condition marked by intrusive, uncontrollable thoughts and compulsive behaviors. Serotonin is a neurotransmitter involved in mood regulation, impulse control, and the ability to shift attention flexibly from one thing to another. When serotonin levels are normal, we can think about many different topics, shifting our focus as needed, maintaining a balanced perspective. When serotonin levels drop, our thinking becomes more rigid, more focused, more difficult to redirect. Thoughts can become intrusive and repetitive, looping back to the same topic again and again, despite our efforts to think about something else. This is precisely what happens in the early stages of romantic love. People report that they cannot stop thinking about the person they are falling for. Thoughts intrude during work, during conversations with others, during activities that would normally absorb their attention. They find themselves mentally replaying interactions, analyzing every word and gesture, imagining future scenarios, unable to fully engage with anything that does not relate to the beloved. This obsessive quality of early love, which poets have described for millennia, turns out to have a clear neurochemical basis in reduced serotonin activity. The obsessive thoughts of early love serve several functions. They keep the beloved at the forefront of consciousness, ensuring that we prioritize the relationship over other concerns. They drive us to analyze social interactions in detail, trying to understand the other person's feelings and intentions. They fuel fantasies about the future, allowing us to mentally simulate how the relationship might develop. And they create a sense of urgency, a feeling that this person is uniquely important, and that we must act to secure the relationship before the opportunity is lost. Interestingly, The low serotonin state of early love may also contribute to the poor judgment that sometimes characterizes this phase. When serotonin is low, impulse control weakens. We become more likely to take risks, to overlook warning signs, to make decisions based on emotion rather than careful reasoning. This is why people in the throes of new love sometimes do things they would normally consider foolish. Quitting jobs, moving to new cities, ending other relationships hastily, making major life changes based on relatively little information about the new partner. The reduced serotonin leaves the prefrontal cortex, the brain's center for rational decision-making, less able to exert control over the emotional impulses generated by deeper brain structures. The connection between low serotonin and obsessive thinking also helps explain why falling out of love or experiencing rejection can be so emotionally devastating. When someone we have been obsessively thinking about becomes unavailable, the obsessive thoughts do not immediately stop. Instead, they often intensify, cycling through memories, analyzing what went wrong, imagining ways the outcome could have been different. The low serotonin state persists. But now the obsessive thoughts are focused on loss rather than anticipation, creating a kind of psychological torment that can be difficult to escape. Medications that increase serotonin levels, such as selective serotonin reuptake inhibitors, commonly prescribed for depression and anxiety, can sometimes dampen the intensity of romantic feelings. Some people taking these medications report that they feel less capable of falling in love, less interested in romance, less able to experience the passionate intensity that characterized their earlier relationships. This observation, while troubling for those affected, provides additional evidence that serotonin levels directly influence the subjective experience of romantic love. As with the other neurochemical changes we have discussed, the low serotonin state of early love is temporary. As relationships mature and the initial obsessive phase passes, serotonin levels return to normal. The constant, intrusive thoughts about the partner decrease. Mental focus becomes more flexible again. The ability to maintain perspective and exercise impulse control improves. This normalization is a sign of healthy relationship development, though it can sometimes feel like a loss, as if the love itself has become less intense. What has actually changed is not the depth of feeling, but the neurochemical profile underlying it. The serotonin story reveals something important about the nature of passionate love. It is, in some sense, a temporary state of altered consciousness. A period when the brain operates differently than it does during normal waking life or in more established relationships. This altered state serves evolution's purposes by ensuring that we become deeply absorbed in the process of pair bonding. But it is not sustainable indefinitely. The brain cannot maintain low serotonin indefinitely without consequences for mental health and daily functioning. The transition away from obsessive love is not a failure, but a necessary adaptation that allows us to maintain romantic bonds while also attending to the other demands of life. The role of our senses in attraction. While neurochemicals provide the internal experience of falling in love, the external world reaches us through our five senses, each of which contributes its own information to the complex calculation of attraction. The brain does not process these sensory streams separately. Rather, it integrates them into a unified perception of the other person, a holistic impression that guides our feelings and choices. Understanding how each sense contributes to attraction reveals the remarkable sophistication of the systems that guide us toward potential partners. Sight is typically considered the dominant sense in human attraction, and for good reason. Humans are highly visual creatures with a significant portion of the brain dedicated to processing visual information. The moment we see someone, our visual system begins analyzing their appearance in ways that happen too quickly for conscious awareness. Facial symmetry is evaluated automatically, with more symmetrical faces generally rated as more attractive. This preference for symmetry may have evolutionary roots. Symmetry can indicate developmental stability and good health, as environmental stressors and genetic problems often manifest as asymmetries. But attraction to faces involves much more than symmetry. We are sensitive to skin texture and clarity, to the size and positioning of features, to subtle proportions like the ratio of face width to height. We respond to expressions, especially smiles, which can transform the attractiveness of a face dramatically. Eye contact creates powerful effects, with sustained mutual gaze triggering activity in brain regions associated with reward and social bonding. Even pupil size matters. We find others more attractive when their pupils are dilated, a response we perceive unconsciously that may signal interest since pupils dilate naturally when we look at something we find appealing. Body attractiveness follows similar principles. We are drawn to body proportions that suggest health and fertility. In women, a waist-to-hip ratio of around 0.7 has been found attractive across many cultures, possibly because it correlates with optimal fertility and fat distribution. In men, shoulder-to-hip ratio and overall muscularity influence attractiveness, traits that may signal strength and ability to provide protection. But again, individual variation is enormous, and cultural factors heavily influence body ideals. The point is not that there is a single standard of physical beauty, but that our visual system has been shaped by evolution to attend to certain cues that may provide information about mated quality. The sense of smell, though often underappreciated in human attraction, plays a more important role than most people realize. Unlike many mammals, humans do not rely primarily on scent for social information, but olfactory cues still contribute significantly to attraction. Every human has a unique scent signature, created by a combination of genetic factors, diet, hormones, and the particular bacterial communities that colonize the skin. This scent, often detectable only at close range, provides information that the brain uses to assess compatibility. Research on human body odor and attraction has revealed fascinating patterns. Studies have shown that people tend to find the natural body odor of potential partners more attractive when those partners have dissimilar immune system genes, particularly at the major histocompatibility complex. This preference may have evolved to encourage genetic diversity in offspring, reducing the risk of immune system weaknesses and increasing the likelihood that children will inherit a broader range of immune responses. Remarkably, women can detect these genetic differences through smell alone, rating the body odor of men with dissimilar MHC genes as more pleasant and attractive. Context matters enormously for olfactory attraction. The same body odor might be attractive in one setting and unattractive in another. Cleanliness, diet, and health all affect body odor. And cultural norms heavily influence what smells are considered appealing. Many people use fragrances to mask or enhance their natural scent, adding another layer of complexity. But beneath all of this, the basic biological scent signature continues to provide information that influences attraction, often without our conscious awareness. Touch is perhaps the most directly powerful sense for building romantic connection. Physical contact, from a light touch on the arm to prolonged embrace, triggers the release of oxytocin and other bonding chemicals. The skin is richly supplied with specialized receptors that detect different types of touch, and certain types of gentle, slow stroking activate nerve fibers specifically tuned to create pleasurable sensations. This is why holding hands, hugging, and other forms of affectionate touch feel so immediately comforting and connecting. Touch communicates emotion and intention with remarkable precision. We can distinguish between friendly touch and romantic touch, between comforting touch and sexual touch, based on subtle differences in pressure, duration, and location. The brain processes touch information in regions that overlap substantially with areas involved in emotional processing, which is why physical contact can affect mood so powerfully. For couples, regular affectionate touch helps maintain emotional connection and continues to trigger oxytocin release even in long-term relationships, supporting ongoing attachment. The sense of hearing contributes to attraction through both voice and language. Voice pitch, tone, rhythm, and accent all influence how attractive we find someone. Lower-pitched voices in men and higher-pitched voices in women tend to be rated as more attractive on average, and though individual preferences vary widely. But voice attractiveness is about more than just pitch. Warmth, expressiveness, humor, and the particular rhythms of someone's speech all contribute to the overall impression. Some people find certain accents especially appealing, demonstrating how cultural and personal factors shape auditory attraction. Language content matters as well, though it works at a more conscious level than the other senses. Shared interests, compatible values, humor, intelligence. All of these emerge through conversation and contribute to attraction. The ability to communicate well, to listen, to make the other person feel heard and understood can dramatically increase attractiveness. This is why many people report that someone became more attractive to them after a good conversation, even if the physical attraction was initially minimal. Finally, taste plays a subtle but real role in romantic attraction. While we do not literally taste potential partners during initial meetings, taste becomes relevant through kissing, which remains one of the most common early romantic behaviors across cultures. A kiss provides a wealth of sensory information, including the taste of someone's mouth, which is influenced by their health, diet, and biochemistry. Some researchers suggest that kissing may have evolved partly as a way to assess mate compatibility through taste and scent, allowing a close-range exchange of chemical information that can guide decisions about whether to pursue the relationship further. Interestingly, the taste of sweet things can actually influence how we perceive potential partners. Studies have shown that people who have just consumed something sweet rate potential partners as more attractive and are more interested in pursuing romance. This effect appears to work through the reward system. Sweet taste triggers dopamine release, creating a positive emotional state that colors perceptions of everything, including the people around us. This is one reason why sharing desserts or sweet drinks on dates has become such a common ritual. The integration of all five senses creates the overall experience of attraction to another person. The brain does not evaluate each sensory channel separately and then add up the scores. Instead, it creates a unified, holistic impression that feels immediate and intuitive. We meet someone and feel attracted, or we do not, and usually we cannot articulate exactly why. What we are experiencing is the result of millions of years of evolution fine-tuning our sensory systems to help us identify compatible partners as efficiently as possible, using every available source of information. Pheromones and hidden signals. Beyond the conscious sensory information we receive from potential partners, there exists a layer of chemical communication that operates almost entirely outside awareness. This is the realm of pheromones and other chemosignals, molecules released by the body that carry information about genetics, health, hormonal status, and reproductive readiness. While the role of pheromones in human attraction remains somewhat controversial among scientists, a substantial body of research suggests that these chemical signals do influence human behavior and mate choice, even if their effects are more subtle than the powerful pheromone responses seen in many other species. Pheromones are chemical substances secreted by an individual that trigger specific responses in other members of the same species. In many animals, pheromones play obvious and dramatic roles. Female moths release pheromones that can attract males from miles away. Dogs use pheromones to mark territory and communicate reproductive status. Ants use them to coordinate colony activities. The question for humans has always been whether we still use this ancient form of chemical communication, or whether we have lost it as our visual and linguistic capacities expanded. The evidence suggests that humans do respond to chemosignals, though perhaps not to true pheromones in the strictest sense. The distinction is somewhat technical. True pheromones are supposed to trigger automatic, stereotyped responses, while chemosignals can influence behavior more subtly and flexibly. Regardless of terminology, research has shown that humans can detect and respond to chemical signals from other people's bodies, and that these signals can influence attraction, mood, and behavior in measurable ways. One of the most studied human chemosignals is androstenedione, a steroid compound found in higher concentrations in male sweat. Women exposed to androstenedione show changes in mood and arousal, becoming more focused and attentive, particularly to emotional information. Their cortisol levels may shift, and brain imaging shows activation in areas associated with emotional processing and social cognition. The effects are context-dependent. Androstenedione has stronger effects when women are in the presence of men or in situations with romantic potential. This context dependence suggests that human chemosignals work not as simple triggers but as modulators, enhancing responses that are appropriate to the social situation. Estradiol, a compound found in female urine, has been proposed as a female chemosignal. Some research suggests that men exposed to estradiol show changes in brain activity and report subtle shifts in mood, though the effects are less consistent than those found for androstenedione. The challenge with human pheromone research is that effects are often subtle, variable across individuals, and highly dependent on context and experimental design. This has led to ongoing debate about whether compounds like androstenedione and estradiol truly function as pheromones, or are simply interesting scent compounds with mild effects on mood. More robust findings come from research on the major histocompatibility complex and its influence on body odor preferences. The MHC is a set of genes that plays a crucial role in immune system function, helping the body distinguish between its own cells and foreign invaders. These genes are highly variable in human populations, and the particular combination someone carries influences their body odor in subtle but detectable ways. The bacterial communities that live on our skin use compounds produced by MHC genes as nutrients, and their metabolic products contribute to our individual scent. Remarkably, humans show preferences for the body odor of individuals with dissimilar MHC genes. This preference has been demonstrated in the famous sweaty t-shirt studies, in which women smell t-shirts worn by men and rate how attractive they find the scent. Women consistently rate the scent of men with MHC genes different from their own as more attractive than men with similar MHC genes. This preference reverses when women are taking oral contraceptives, which alter hormonal profiles and may shift mate preferences in ways that reflect the hormonal state of pregnancy rather than fertility. The preference for MHC dissimilar partners makes evolutionary sense. Choosing a mate with different immune system genes increases the likelihood that offspring will inherit a more diverse and robust immune system, better able to fight off a wider range of pathogens. This form of mate choice, guided entirely by scent and operating outside conscious awareness, represents one of the oldest systems of genetic compatibility assessment in the animal kingdom, and it appears to still function in humans despite our heavy reliance on other forms of social information. Other chemosignals may communicate information about emotional state. Research suggests that humans can detect the scent of fear and anxiety in others' sweat, and that exposure to these scents can trigger corresponding emotional responses or heightened vigilance. Conversely, scents associated with happiness or calm may have subtly positive effects on the mood of those who smell them. While these effects are not specific to romantic attraction, they demonstrate that chemical communication about emotional state is ongoing in human social interactions, providing a constant background stream of information that may influence how we feel about the people around us. The mechanisms through which humans detect chemosignals are still being investigated. Some researchers believe that the vomeronasal organ, a specialized structure that detects pheromones in many mammals, may still function in humans, though in a reduced capacity. Others argue that human pheromone detection occurs primarily through the ordinary olfactory system, the same system we use to smell everything else. Brain imaging studies show that exposure to compounds like androstenedione activates areas of the brain involved in social cognition and emotional processing, not just the primary olfactory regions, suggesting that chemosignal processing may involve dedicated neural pathways. Individual variation in sensitivity to chemosignals is substantial. Some people appear to be much more sensitive to androstenedione and similar compounds, while others are essentially anosmic, unable to detect them at all. This variation may have genetic basis, with different versions of olfactory receptor genes affecting whether someone can perceive particular compounds. It may also be influenced by experience, hormonal state, and context. Women's sensitivity to androstenedione varies across the menstrual cycle, being highest near ovulation when fertility is greatest. The role of pheromones and chemosignals in human attraction, while real, should not be overstated. We are not slaves to chemical signals, nor do pheromones override our conscious preferences and choices. Rather, they provide one additional stream of information, a subtle influence that works alongside visual, auditory, and social cues to shape our responses to potential partners. In a world where perfumes, deodorants, and other scent products are ubiquitous, natural body odor plays a smaller role in mate choice than it would have in ancestral environments. Yet the systems remain, ancient and largely hidden, continuing to provide information that the brain uses, consciously or not, to navigate the complex landscape of human attraction. Oxytocin and vasopressin, the bonding chemicals. If dopamine creates the thrill and obsession of early attraction, oxytocin and vasopressin are the chemicals that transform that intense but fragile connection into lasting attachment. These two neuropeptides, structurally similar molecules that function as both hormones and neurotransmitters, are central to how romantic love deepens and endures over time. They are often called bonding chemicals, and their effects on the brain help explain why long-term relationships can feel secure and comforting, even after the initial passionate intensity has faded. Oxytocin has been called the love hormone, though this label is somewhat misleading because oxytocin is involved in many forms of social bonding, not just romantic love. It plays crucial roles in mother-infant bonding, in trust and cooperation, in recognition of familiar individuals, and in the formation of social memories. What makes oxytocin particularly relevant to romantic love is that it is released in large quantities during intimate physical contact, especially during sexual activity and orgasm, and its effects on the brain promote the formation of lasting emotional bonds. The oxytocin system works differently from the dopamine system. Where dopamine creates excitement and craving, oxytocin creates calm and contentment. Where dopamine focuses attention intensely on the beloved, oxytocin broadens the experience to include feelings of safety, trust, and deep comfort. Oxytocin is released during hugging, during gentle touch, during moments of emotional intimacy, and during sex, creating a neurochemical association between physical and emotional closeness with this specific person and feelings of well-being. Research on oxytocin has shown that it affects multiple brain regions important for social behavior. It modulates activity in the amygdala, reducing fear and anxiety responses, which helps explain why being with someone we love can feel like a safe haven. It influences the reward circuits, working alongside dopamine to create positive associations with the partner. It affects the prefrontal cortex, influencing how we think about and interpret the actions of those close to us, generally promoting more charitable and trusting interpretations. One of oxytocin's most important effects is its role in the formation of social memory. When oxytocin is present during social interactions, The brain encodes those interactions more deeply and forms stronger associations between the person and positive emotional states. Over repeated interactions accompanied by oxytocin release, the neural representation of the partner becomes strongly associated with feelings of comfort, safety, and pleasure. This is the neurological basis of attachment. The brain has learned through oxytocin-mediated processes that this specific person is a source of well-being. Oxytocin levels increase significantly during physical intimacy. Touch triggers oxytocin release, creating a feedback loop where affection prompts oxytocin, which promotes more affection. Sexual activity is particularly powerful, with oxytocin levels spiking dramatically during orgasm for both men and women. This surge of oxytocin during the most intimate moments of a relationship helps cement the emotional bond between partners, quite literally rewiring the brain to associate this person with intense, positive feelings. Interestingly, oxytocin may also have a darker side. While it promotes bonding with partners, it can simultaneously increase defensiveness toward outsiders, a phenomenon sometimes called the tend and defend response. Oxytocin can make people more loyal to their in-group while becoming more suspicious or even aggressive toward those perceived as threats to the group. In the context of romantic relationships, this might manifest as increased jealousy or possessiveness, though these effects vary widely across individuals and situations. Vasopressin, while less famous than oxytocin, plays an equally important role in romantic attachment, particularly in men. The two neuropeptides are structurally similar and have overlapping effects, but vasopressin appears to be especially important for male bonding and for behaviors associated with mate guarding and territoriality. In animal studies, particularly research on prairie voles, a species that forms monogamous pair bonds, vasopressin has been shown to be essential for male attachment to female partners. In humans, vasopressin is released during sexual activity and physical intimacy, much like oxytocin, and it promotes similar feelings of attachment and bonding. But vasopressin also appears to contribute to more protective, possessive feelings toward one's partner. It may underlie the motivation to guard the relationship, to defend the partner from threats, and to maintain the bond over time. Some researchers have suggested that individual differences in vasopressin receptor genes may influence how readily men form committed romantic relationships. Though this area of research is still developing, the combination of oxytocin and vasopressin working together in the brain creates the neurochemical foundation for long-term attachment. As a relationship matures and these chemicals come to play a larger role relative to dopamine, the subjective experience of love changes. The frantic energy and obsessive preoccupation of early love give way to something calmer, but no less significant. A deep sense of connection, trust, and interdependence. The partner becomes a source of comfort rather than primarily a source of excitement, a secure base from which to navigate the world. This transition is sometimes misinterpreted as falling out of love, when in fact it represents a different form of love emerging. The brain is shifting from the short-term intense bonding mechanism designed to bring two people together to the long-term maintenance mechanism designed to keep them together. Both forms are love. Both are mediated by specific neurochemicals. but they feel quite different subjectively. Understanding this transition can help couples navigate it successfully, recognizing that the change in feeling does not signal a problem, but rather the deepening of the relationship. Touch remains important for oxytocin and vasopressin release throughout a relationship's duration. Couples who maintain regular physical affection, holding hands, hugging, cuddling, continue to stimulate the release of these bonding chemicals, which helps sustain emotional connection over years and decades. This is why physical intimacy, even non-sexual touch, is so important for relationship maintenance. It is not just symbolically important. It is neurochemically necessary for maintaining the brain changes that underlie attachment. Brain regions activated by love. While neurochemicals provide the language of love, communicating between neurons through chemical signals, the story is incomplete without understanding the brain regions where these chemicals act. Falling in love activates a specific network of brain areas, some ancient structures shared with other mammals, and some more recent evolutionary additions specific to primates and humans. Together, these regions create the complex experience we call romantic love. The ventral tegmental area, or VTA, is ground zero for dopamine-driven romantic love. This small region in the midbrain contains neurons that produce dopamine and send their projections to many other brain areas. When someone looks at a photograph of a person they love, the VTA shows dramatically increased activity. This activation reflects the production and release of dopamine that creates the pleasure and motivation characteristic of romantic attraction. The VTA is part of the brain's reward system, the same circuitry that responds to food when we are hungry, to water when we are thirsty, and to addictive drugs. Love commandeers this ancient motivation system, focusing it on a social target. The caudate nucleus, part of the brain's basal ganglia, is one of the primary targets of dopamine projections from the VTA. This region is involved in reward processing, goal-directed behavior, and the formation of habits. Brain imaging studies consistently show strong activation in the caudate when people view pictures of their romantic partners, particularly in the early, passionate stages of love. The caudate is helping to translate the dopamine signal from the VTA into motivated behavior, driving the urge to seek out and spend time with the beloved. The nucleus accumbens, another component of the reward circuit, also activates strongly during romantic love. This region is crucial for experiencing pleasure and reward, and its activation correlates with the subjective feeling of euphoria that love creates. The nucleus accumbens receives dopamine from the VTA and processes this signal to create the conscious experience of something being pleasurable and worth pursuing. Its involvement in romantic love reveals why being in love feels so rewarding, why the presence or even the thought of the beloved creates such positive feelings. Interestingly, brain regions associated with negative emotions show decreased activity when people experience romantic love. The amygdala, which processes fear and threat detection, shows reduced activation when someone looks at their romantic partner. This is particularly striking because the amygdala normally activates when we look at faces, as part of its role in rapid social threat assessment. The reduction in amygdala activity during romantic love suggests that the brain has classified the partner as safe, trustworthy, non-threatening. This neural quieting of fear systems helps create the sense of security and comfort that allows intimacy to develop. Similarly, regions of the prefrontal cortex associated with negative social judgment and critical evaluation show decreased activity during romantic love. The brain essentially suspends some of its normal evaluative functions when we are looking at someone we love, which helps explain why love can feel blind to flaws, and why we often see our partners through rose-tinted glasses, at least initially. This temporary suspension of critical judgment may serve an important function, allowing bonds to form without being undermined by the kind of skeptical evaluation we normally apply to others. The anterior cingulate cortex, a region involved in attention, emotion regulation, and pain processing, shows increased activity in romantic love. This area may be involved in the intense focus on the beloved that characterizes passionate love, helping to direct attention and cognitive resources toward relationship-relevant information. Some researchers have also suggested that activation in this region might relate to the mild anxiety and uncertainty of early love, as the anterior cingulate is involved in detecting conflicts and unexpected events. The insula, a region buried deep within the folds of the cortex, also activates during romantic love. The insula is involved in emotional awareness and in translating bodily sensations into conscious feelings. Its activation may contribute to the physical sensations of love, the butterflies, the racing heart, the warmth, by bringing those bodily signals into conscious awareness. The insula helps us feel love not just as an abstract emotion, but as a physical experience within the body. One of the most fascinating findings from brain imaging research is that different patterns of activation correspond to different types of love. Early, passionate, romantic love activates the reward circuits very strongly, with high levels of activity in the VTA, caudate, and nucleus accumbens. Long-term attachment shows a somewhat different pattern, with continued activation in some reward areas, but also increased activity in regions associated with oxytocin and vasopressin signaling, including the hypothalamus and other areas involved in pair bonding. Maternal love activates yet another pattern, with strong activation in areas associated with oxytocin, but less activation in the dopamine-rich reward circuits. These patterns suggest that love is not a single brain state, but a family of related states, each with its own neurochemical profile and pattern of brain activation. Passionate romantic love, long-term attachment, parental love, and friendship each engage overlapping but distinct neural circuits. What they share is involvement of the brain's social bonding systems. What differs is the particular balance of neurochemicals and the specific regions most strongly activated. The prefrontal cortex, the brain's center for complex thought, planning, and self-control, plays a complex role in romantic love. On one hand, certain prefrontal regions show decreased activity during passionate love, as we have discussed, potentially contributing to the impulsive, less rational aspects of falling in love. On the other hand, other prefrontal areas remain active and may be involved in the cognitive aspects of love, thinking about the partner, planning future interactions, making relationship decisions. The prefrontal cortex helps integrate emotional responses from deeper brain structures with rational thought and social knowledge, allowing us to navigate relationships with some degree of conscious control even as powerful emotional currents pull us along. The hippocampus, essential for memory formation, works closely with the reward system and emotional centers to encode memories related to the beloved. Every significant interaction, every meaningful conversation, every shared experience gets encoded with emotional tags that make these memories particularly vivid and easily recalled. The hippocampus ensures that the relationship has a history, that each partner builds a detailed knowledge of the other that can inform future interactions and deepen the sense of knowing and being known. The evolution from passion to companionship. One of the most common questions people have about love is why the intense feelings of early romance inevitably change over time. The passionate love of the early months, with its obsessive preoccupation, constant excitement, and emotional intensity, typically evolves into something calmer and more stable. This transition can be unsettling, leading some to worry that love is fading, that the relationship is failing, that perhaps they have fallen out of love. Understanding the neurochemistry behind this transition reveals that it is not only normal but necessary for relationships to develop in this way. The passionate love of the early stages simply cannot be maintained indefinitely. The neurochemical state it involves, high dopamine, low serotonin, elevated cortisol, and norepinephrine, is metabolically expensive and somewhat incompatible with normal daily functioning. The brain cannot sustain elevated stress hormone levels long-term without negative health consequences. The obsessive, single-minded focus that low serotonin creates would prevent us from attending to work, to other relationships, to basic life maintenance. The sleep disruption, the loss of appetite, the constant emotional intensity. All of these take a toll that the body cannot bear indefinitely. What happens over time, typically within 1 to 2 years, is that the neurochemical profile of the relationship shifts. Dopamine levels remain elevated when with the partner, but not to the extreme degree of early love. The brain habituates to the reward of the partner's presence, responding more moderately but still positively. Serotonin levels return to normal, allowing thought processes to become less obsessive and more balanced. Cortisol returns to baseline, signaling that the relationship no longer represents an uncertain crisis but has become a reliable source of support. Norepinephrine moderates as well, reducing the physical anxiety symptoms that accompanied early attraction. As the changes occur, oxytocin and vasopressin come to play increasingly central roles. The repeated experiences of intimacy, physical affection, and emotional support have gradually rewired the brain to associate the partner with feelings of safety, comfort, and deep attachment. The neural representation of the partner has shifted from being primarily associated with excitement and reward to being associated with bonding and security. This represents a successful transition from attraction to attachment. The subjective experience of this transition is that passionate love transforms into companionate love. The constant need to be together may moderate into a comfortable rhythm of togetherness and independence. The obsessive thoughts about the partner give way to a more integrated awareness, where they remain important but do not dominate every moment. The intense physical and emotional arousal of early love settles into a deep affection and warmth. The relationship feels less like a roller coaster and more like a safe harbor. This transition is not a loss, though it can feel that way if we believe that passionate intensity is the only authentic form of love. In fact, companionate love has its own neurochemical basis, its own pattern of brain activation, and its own profound significance. Studies of couples in long-term happy relationships show that they still display activation in reward-related brain regions when viewing pictures of their partners, though the pattern of activation differs somewhat from that seen in new love. They show high levels of oxytocin and vasopressin signaling, reflecting strong attachment. They report deep satisfaction, contentment, and security in their relationships. Importantly, the transition from passionate to companionate love does not occur at a fixed pace or to the same degree in all relationships. Some couples maintain higher levels of passion for longer. Some transition more quickly to companionate love. Some find ways to periodically rekindle passion within the context of stable attachment. The specific trajectory depends on many factors. How often partners experience novel experiences together, how they communicate, how they handle conflict, how much physical affection they maintain, and their individual neurochemistry and attachment styles. One of the factors that can help maintain passion in long-term relationships is novelty. The dopamine system is particularly responsive to new and unexpected experiences. Couples who regularly engage in novel activities together, who travel to new places, who try new things as a pair, often maintain higher levels of romantic passion than couples whose routines become too predictable. The brain interprets these novel experiences while with the partner as part of the reward associated with the partner, helping to sustain dopamine-driven attraction alongside oxytocin-mediated attachment. Physical intimacy remains crucial throughout the evolution of love. Sexual activity continues to trigger releases of oxytocin, vasopressin, and dopamine, maintaining the neurochemical bonds that support attachment. Couples who maintain regular sexual intimacy throughout their relationships tend to report higher satisfaction and stronger feelings of connection. Non-sexual physical affection is equally important. Holding hands, hugging, cuddling, and other forms of touch continue to stimulate oxytocin release, reinforcing attachment even in the absence of sexual activity. Communication and emotional intimacy also support the maintenance of love through its various phases. Feeling understood, valued, and supported by a partner activates reward centers in the brain and promotes continued oxytocin release. Couples who continue to share their inner lives with each other, who maintain curiosity about one another, who support each other through challenges, keep their neural bonding systems active and healthy. Love, in this view, is not a static state but an ongoing process that requires continued engagement and attention. The ability of love to evolve and change while remaining love is one of its most remarkable features. The passionate love of early romance and the deep companionate love of long-term partnership are neurochemically distinct states. Yet both are authentic forms of love. Both create powerful bonds. Both provide meaning and fulfillment. Understanding that love naturally transforms over time can help couples navigate the transition without panic. Recognizing that the fading of initial intensity is not a sign of failure, but of successful bonding. As we come to the end of this quiet exploration through the chemistry of love, allow yourself to rest with the knowledge we have gathered tonight. We have journeyed through the intricate networks of the brain, following the paths of dopamine as it creates pleasure and craving, watching cortisol rise in the sweet stress of new attraction, observing serotonin dip as thoughts become beautifully obsessive. We have seen how oxytocin and vasopressin weave two people together through touch and intimacy, how the ventral tegmental area glows with reward when we see the face of someone we love, how the amygdala quiets its warnings when we feel safe in another's presence. The chemistry of falling in love reveals that this profound human experience is both deeply biological and utterly transcendent. It is biological in that it arises from molecules and neurons, from ancient brain structures shaped by millions of years of evolution, from systems we share with other mammals who also form pair bonds and care deeply for their mates. Yet it is transcendent in what it creates. The capacity for two separate beings to form a connection so powerful that they become, in many ways, a single system, each person's nervous system attuned to the other's state, each person's well-being dependent on the other's presence and care. Understanding the neuroscience of love does not diminish its magic. If anything, it deepens our appreciation for how exquisitely the human brain is constructed, how elegantly evolution has solved the problem of bringing people together and keeping them together across years and decades. The same reward system that motivates us to seek food and water also motivates us to seek connection and intimacy. The same stress system that protects us from danger also drives us to take the emotional risks necessary for love. The same bonding chemicals that tie mother to infant also bind romantic partners in relationships that can last a lifetime. Love is chemicals, but it is also choice. The neurochemistry creates the feelings, the motivation, the pleasure and pain, but we still decide how to act on those feelings. We choose whether to pursue a relationship or walk away. We choose whether to invest in maintaining connection or allow it to fade. We choose whether to open ourselves to vulnerability or protect ourselves from potential hurt. The chemistry provides the substrate, but the story we create from it is ours. If you found peace in this journey through the science of love, I gently invite you to like and subscribe to this channel. Your support allows these explorations to continue, helping others find their way to this quiet space where knowledge becomes a pathway to rest. Share your thoughts in the comments below if you feel moved to do so, or simply carry what resonates with you into your own reflections. For now, let everything settle. Let your mind release these thoughts, allowing them to drift like leaves on water, floating away into the quiet darkness of approaching sleep. You have learned something tonight about the hidden machinery that makes us human, about the invisible forces that draw us to each other and bind us together. But you need not hold on to any of it now. Simply breathe. Feel the weight of your body supported. Notice the softness of this moment, the gentle invitation to let go completely. Love is chemistry, yes, but love is also mystery. And mystery is a beautiful place to rest. Sleep well, and may your dreams be full of connection and warmth. Good night.